All right, thanks so much for putting the paper on the program, especially the two organizers that are not part of the project, because Philippe is one of the co-authors. Exactly. So this paper is about green growth, and what we mean by green growth is that there's the hope that over the coming decades we're going to find ways to produce our current levels of consumption and then some in non-polluting ways, and that's going to require innovation. And if we want to measure our success in terms of achieving green growth, one thing to look at is how are we currently innovating? Are we seeing a switch away from non-green innovation towards green innovation? Now, measuring green innovation, as we saw earlier today, is difficult, but the thing that we often look at is patents. Right? So if you look at the fraction of all patents that is related to climate change mitigation, for a long time that was growing. And that's what this graph shows. So this graph on the vertical axis plots the percentage of all patents that is green by the OECD definition. So green patents, the OECD has gone line by line through IPC codes and has classified patents as green or not based on whether they're related to climate change mitigation and the likes. So examples of green patents would say be technologies related to LED lights or to batteries of electric vehicles. Nuclear energy is also in there. So if we have any Germans in the room, that is considered green. And so during the 1990s and 2000s, you see that the share of all patents that's green starts to accelerate. It starts rising. It goes from less than 3% to more than 6% of patents. Now, this is just globally, so we're just putting all of PatStat together. But if you look within countries, you see these trends. If you weigh by measures of quality, like citations, the increase is even stronger. But what we want to talk about in this paper is that since 2012, that growth seems to have flatlined. The share of all patents that's green doesn't increase after 2012. In fact, it stays flat all the way until 2018, and we just added 2019 to this, and it looks exactly the same. And that's roughly where what we can do ends, because we're looking at accepted patents, right? So there's a lag with which you can actually measure patents. Now, 2012, that's a couple of years after the biggest financial shock of the century, right? It's a couple of years after the global financial crisis. And so the question that we ask in this paper is whether it's the case that green technologies or new technologies more general are more susceptible to financial disruptions. What we propose in this paper is a framework where that's going to happen even if there is no intrinsic difference in the ability of firms to fund green innovation versus non-green innovation. Okay? So how is that going to work? It's going to come from two assumptions. First, we're going to assume that young firms are more financially constrained than old firms. Okay? That's probably the most uncontroversial assumption of the two. So the second assumption is that innovation is directed in the sense that firms choose how much of their R&D is spent on developing green innovations versus non-green innovations, and that directed innovation is path dependent. And by path dependence, we mean that firms build up expertise in technologies that they have a successful track record of innovation in. Now, these two assumptions together are going to mean that when the economy is in transition, so not in the steady state, but when the economy is in transition from a world in which most production is polluting to a world in which most production is green, at the early stages of the transition, young firms are going to have a comparative advantage in green innovation. And that's because at the start of the transition, these young firms, right, because they're not locked in to these polluting technologies yet, are going to do a greater share of all green innovation, right? But because young firms are more financially constrained, when there is a financial crisis at the onset of a transition, those two assumptions together are going to give this negative effect of a financial shock on green innovation. And therefore, you endogenously get sensitivity of green innovation to a shock during the transition. But it purely comes from the identity of the firms that self-select into green innovation. So it's not just theory. We're going to provide you some empirical evidence. We're going to have a small sample of German firms today where we show evidence that indeed young firms are the ones that cut their innovation, and pre-global financial crisis, younger firms were responsible for a large share of green innovation. As we speak, Antonin is repeating this analysis on the universe of French firms, but today we're just going to have results on German firms. So we then use the empirical evidence to quantify the model, and we show that on impact, we explain up to 47% of the slowdown of green innovation with this mechanism. There's also a more general lesson of this paper, because nothing in the mechanism that I just outlined has to be specific to green technology. Any technology that is subject to path dependence means that when the economy transitions, right, to a new steady state in which the new technology is going to be more dominant, young firms self-select into the new technology, and young firms, given that they're financially constrained, are going to cut their R&D when there is a financial shock, right? So potentially, in general, tightening of financial constraints can be very costly when the economy is in transition. The literature review is basically everyone in the room, including our discussant. So I'm sure Ufuk will highlight some of the relationships to his own work, but I'll leave that in the interest of time. Okay, so I'm going to cover all parts of the papers today until the chair's alarm is going to ring. Right, so framework. This is all standard, the setup that we have, but I'll briefly go over it in case you don't know this kind of model. So we have a clatocortum type model, very simple on the household side. The household derives large utility from consumption. It supplies labor inelastically. There's a continuum of goods in the economy, and goods throughout the presentation are going to be indexed by J. Now, what's different compared to some of the models that you might be familiar with is that firms don't just produce one of these goods, they might produce multiple of these goods. So firms are indexed by I and they potentially produce multiple goods. Now, each product in this economy can be produced with a clean or a dirty technology, and what kind of technology a firm produces with depends on the kind of patent that it owns. So firms are going to have patents to produce a subset of all of the goods in the economy, and a patent enables a particular firm to produce a product with either the clean or the dirty technology, right? So with either of the two technologies in the set H. Now, patents grant firms the right to produce goods with some level of quality, and the quality at which firm I can produce good J is QIJ, where the superscript refers to whether the patent is green or non-green. So what is quality? Well, quality determines how much utility the household derives from a good. And you can see that from the aggregator here. So this is GDP. We have a Cobb-Douglas aggregator. The integral is over all of the products that we have in the economy. And within that, we just have the total output by all firms with a patent to produce good J. So total output for a good is just a sum of total production, of the number of units of goods that firms sell, multiplied by the quality of the good. So quality means more utils for a given unit of a good. Now, multiple firms are going to have the patent to produce a good, but in equilibrium, there's only going to be one producer for each product, and that's going to be the firm that offers the highest quality compared to the price that it charges. Okay, and firms are going to compete by tron, so that's going to be the only firm that produces in equilibrium. So that's all standard. Okay, all of that is actually the case in clatocortum type models. What is different is that we have these two production technologies. We have a dirty production technology or a clean production technology, and here we're going to follow Ufuk's 2016 paper. So we assume that to produce a good with a clean technology, you only require labor as an input. It's just going to be linear in labor. If you are producing with a dirty technology, you produce with two inputs, labor, that's LD on this slide, as well as some polluting input, O, for say oil, and the production function is a Cobb-Douglas in these two. That's very convenient because it means that I can write optimal use of oil as a function of how much labor I get to use, as well as the relative price of these inputs. So wage is the price of labor, and PO is the price of oil. And so I can reinsert this first order condition into the production function, and so I can express the amount of dirty production in terms of how many workers I employ in dirty production, and some constant in front of that, and that gives you the relative efficiency of dirty versus clean production. Okay, so this is the relative productivity of dirty production. So the marginal cost of producing a unit of a good with the clean technology, that's just a wage. The marginal cost of producing with the dirty technology, that's going to be wage times P tilde, where P tilde is just the inverse of this term. So what we're going to do in this paper, because this paper is all about the transition, right? We're going to look at a financial crisis that happens during a transition, is over time, P tilde is going to increase, right? So any increase in carbon taxes or somewhat less directly a change in consumer preferences or something of the kind, we're all going to load that on P tilde. So we're going to say P tilde is going to grow over time. When firms see that, they want to redirect their efforts towards clean innovation. So how does innovation work? Innovation is a Poisson process, so firms choose the arrival rate of patents that are clean and dirty, and that's how firms expand the set of products that they get to produce. Now, a bunch of things are standard here. So it's an endogenous growth model, which means that to get more patents, you have to hire more researchers. That's RD here. There are some cost parameters, but importantly, the amount of patents that you get per R&D worker depends on your track record of either dirty or clean R&D. So remember, the superscripts are either clean or dirty. So you separately choose how many clean patents to get and how many dirty patents to get. And the number of clean patents or dirty patents that a clean researcher delivers is going to increase in the number of clean products that I already produce. And that's going to introduce path dependence in the model. So a firm that has a track record of green innovation is going to produce a lot of clean goods, and so it gets more patents per unit of research in the clean technology. Okay, so that differs from the standard model in which we just say it depends on your overall products that you currently produce, but we're saying whether you're good at green innovation or good at dirty innovation, that's tied to your current production, right? So just because you're currently a producer of oil, right? You're drilling up oil, obviously that makes you better at coming up with better oil drills, doesn't make you a better researcher in solar panels, right? And so that's something that people have shown in the data, right? So Philippe's 2016 paper. There's also a recent paper by my colleague Eugenie at LSE that shows that even if you look at the individual inventor level, even when the incentives to conduct research switch away from dirty towards green, people don't switch their research activity. Right? And the reason for that is that the skills required to be a green innovator are just orthogonal to the skills required to be a dirty innovator. Okay? If you guys wanted to be sociologists, right, the cost of that the costs are high. Okay? It's an extreme pivot, I guess I should say. We have a separate technology for entry. Let me skip this. Let me talk about what we do on the financial side. On the financial side, we're very simple. Okay? We're simplistic even. We're just going to assume that younger firms are more financially constrained. Now, we have a micro foundation for it, and a micro foundation is monitoring costs. If you're a new firm, lenders don't know yet how to observe your quality as a lender, and so it's more expensive for you to borrow. But what we're going to do practically, given that we're just going to calibrate this directly from the microdata, is we're going to say a firm is born young. Young firms are financially constrained, and that just means that when there's an aggregate financial shock, right, their own costs of getting funding are more elastic to that, right? You need to pay these costs in order to do R&D. So we're just going to treat financial costs as a parameter, and we're going to say that during a financial crisis, the young firms have a much bigger tightening to their costs than other firms. So over their life cycle, firms mature. They go from the lowest maturity status, K1, to higher levels of maturity, and in that, their elasticity of financing costs to a financial shock decline. Okay. All right, so that's the presentation of the model. So just in terms of optimization, there's static optimization and dynamic optimization. Statically, firms choose the price that they set. It's a model where we have a Cobb-Douglas aggregator, so the firm with the highest quality patent is going to limit price its closest competitor. Now, because the marginal costs depend on whether you're a clean or a dirty producer, what the price that I'm going to charge and the markup that I'm going to charge is going to depend on whether I'm a clean or a dirty producer and vice versa for my competitor. So if I'm a clean producer and my closest competitor is a dirty producer, right, my markup is going to be my quality difference compared to the closest competitor, that's lambda, times the relative cost advantage that I have. So the more expensive it is to produce with the dirty technology, the higher the markup is for clean production, and vice versa if I'm a dirty producer or a clean producer. Okay? So this is going to be a model. Sometimes people in the UK, everyone says we need to tax flying more because it's going to make trains more affordable. Right? That doesn't happen. Right? If you make flying more expensive, so you raise P tilde, actually the clean producers are going to jack up their price. Right? So actually the train becomes less affordable. Right? Eurostar is not a charity. Neither is it in this model. So, and by the way, if both firms have the same technology, then the markup is just a quality difference. That's a static maximization. Then we have the dynamic optimization. We have a first order condition for research and development. So the X here is the optimal innovation rate. Again, you choose it separately for clean and dirty production. Depends on a bunch of cost parameters, but importantly, it depends on the value, right, of having a particular patent. So this is the value of either having a clean patent or a dirty patent, and this is your innovation rate. Now, importantly, your optimal innovation rate depends on how many products you currently produce of a particular product, right? So even if at the start of a transition, we jack up the value of having a clean patent, if I don't do anything related to clean technology yet, it's very hard for me to start developing clean patents, right? Okay, so what happens over a transition? So say we start in a steady state where firms are predominantly using dirty technologies. We're going to start the transition by having a gradual increase in P tilde. So that's going to raise the markup of clean production. It's going to lower the markup of dirty production. And that is immediately going to affect the value of owning a clean patent, right? So when you increase P tilde, we want to have clean patents. We want to switch our innovation towards clean technology. But firms that don't own any green patents yet require time to start developing clean, to start getting a stock of clean products, right? So initially, the first firms that are going to exploit this increase in the value of being clean producers are going to be the firms that have just entered, right? They're still nimble. They can just direct their innovation towards green or dirty based on what is more profitable. So at the start of a transition, most of the firms that have the capacity to innovate in green technology are going to be the young firms. But it means that when there is a financial shock, which we model as a bigger increase of the shadow price of R&D for the young firms, right? The firms that are going to be hit by that are the young firms. And so that's why you get an overall slowdown in green innovation. So I'll be very short on the empirics, given that we only have a few minutes left. We have currently in the paper, we have just German firms. Again, we're repeating this for French firms. What we show in the microdata is that firms that are more exposed to the global financial crisis, they cut their green patents and not their non-green patents. We measure exposure to the global financial crisis through firm bank links. So we rely on the fact that firms tend to borrow from the same banks consistently over time. And we're going to use the fact that in Germany, there was one bank that between 2009 and 2013 gradually reduced its corporate loan portfolio because it had very bad mortgage-backed security investments in the US. So these firms had less credit supply, and we're going to look at how that affects their green patents and their non-green patents. So on the left-hand side, we have the effect of being a firm that is more exposed to the global financial crisis on your green patenting. Here we have the effect on your non-green patenting, and we're estimating this with a PPML regression. And what you see is, so Commerzbank starts cutting its lending supply between 2009 all the way to 2013, and what you see is that this negatively affects green innovation, but not its non-green innovation. But this effect turns out to be driven by composition, because if we only look at younger firms, those are the ones that are cutting their patents to begin with. So here we do a triple diff and diff. We look at the effect of being exposed to the bad bank, Commerzbank, on your green innovation post-crisis for firms that are below median age versus firms that are above median age. Okay? Now, I say younger and not young here because the average age here below median is something like 14 or 15 years. So these are not just startups, but we've got 600 firms. It's not like we can do 20 categories. So what you see is that the triple diff is very significant, and the simple coefficient for Commerzbank exposure even becomes positive. So that means that only the young firms, they cut their green innovation in response to a Commerzbank, in response to being hit by the shock. If we look at the role of young firms in green innovation, it turns out that prior to the global financial crisis, these younger firms were responsible for 70% of green patents. For non-green patents, they were only doing 20% of innovation. So the younger firms were doing green innovation, the younger firms cut their overall patenting, and therefore you get this negative effect of the crisis on green patenting. I'm going to skip my cool monetary policy graphs, but we can talk about them afterwards. Briefly, in a nutshell, what do we do when we quantify the model? So when we quantify the model, we match the initial steady state for Germany. We impose a transition where gradually there's going to be an increase in green innovation driven by an increase in P tilde, this relative profitability of green production. And then we're going to have a financial shock in the middle of that transition. So let me skip the details on the quantification and just show you the results. So black line here in the background, that's the increase in green production over the transition. The transition lasts 40 years. And we have a 2-year steep financial crisis in 10 years after the start of the transition. So our transition starts in 1998, which is when the Kyoto Protocol was enacted. So 10 years after that, that's 2008. And what you see is that there's a slowdown, right, in green production. We can zoom in to show that it's actually sizable. And if you compare the rate of change, right, in the old transition versus transition when there's been a financial crisis, there's a temporary 47% decline in the speed of transition. Now, in the data, right, the transition flatlines. Right? So that's why we say this is a 47% reduction. Final slide, right? This is just the impulse response. So we're looking at the deviation of green production from trend as a result of this financial crisis. And I wanted to show you this graph both for when the economy is in transition versus when the economy is in steady state. In the steady state, a financial shock doesn't affect green innovation more than dirty innovation. And that's just because the average age of a green innovator or a dirty innovator in the steady state is going to be the same. Right? So there's no effect. But because the economy is in transition, it's going to be sensitive to financial constraints. And that's what I'll add. Thank you.
Thank you, Martin. So thank you very much for having me on the program to discuss this very exciting paper. And I completely share Ben's sentiment. You know, by the time I started PhD, Zvi wasn't around anymore, unfortunately, but he was everywhere, right? Especially, you know, when you live in Cambridge, you felt his fingerprints everywhere. We used his data. We used, you know, we built on his ideas, and it's an honor to be part of this beautiful conference. So the paper is focusing on a very important topic, and the paper studies the impact of financial disruptions on green innovation. It's a very important topic, and you know, if you think about, indeed, Martin did a fantastic job, and he made my life much easier. Super crystal clear presentation. So when you think about the idea that you know, the world is going through creative destruction and new ideas are introduced by newcomers, then of course, you know, green transition is probably the poster child for creative destruction. So that's why, you know, these new technologies, these radical technologies will be introduced mostly by new entrants. That's why, you know, it's very easy to buy the argument at the face value. And the paper is also, I might be biased on that, but it's also taking a nice theoretical angle. So I think it's a great paper. It's still, you know, advanced work in progress. So hopefully, you know, some of my comments can help shape the paper and make it even stronger. So it's analyzing the challenges and opportunities for young and established firms during this transition. And the idea is that older firms are often entrenched with traditional, in this case, dirty technologies. And the main hypothesis is that younger firms have a comparative advantage in pioneering green technologies, and financial frictions disproportionately affect younger firms. And I put the smaller in parentheses, and I'm going to come back later, and potentially causing lasting environmental impact. And Martin already talked about this graph, and this is the main motivating graph in the paper. And they are, you know, the paper is building on the observation that after the financial crisis, there has been a slowdown in green patenting in general. So in a nutshell, this is the theory, and so in a nutshell, this is the theory. So there's a final good, and this final good can be produced in two ways. So there's a clean variety and there's a dirty variety. And within each varieties, there are different qualities that are being introduced over time. And for clean technology, this is the production function. There's only labor that's being used. For dirty technology or dirty output, there's both labor and oil that's being used. So, and then this is the R&D technology. You need to, you know, once you want to go from statics to the dynamics, you need to introduce an innovation technology. And this is the standard innovation technology in this literature. But I think the critical part here is this N term. So, you know, all this existing R&D literature from, you know, 80s and 90s, they were estimating this portion of the R&D technology, but the recent models, especially after Clet and Kortum, have introduced also the role of existing expertise on certain fields. So if I'm more experienced in certain fields, then this is going to make me even more productive. And this structure here is nice because it also allows larger firms also to scale up, and that kills this very fast diminishing returns in firm size. And that's why this was not only very attractive, but I think it was also empirically relevant. And this paper is also introducing this R&D technology. But the important argument here is that established firms have a large N in old dirty technologies, basically. So they spend so much time already innovating a lot of dirty technologies or dirty energy related technologies. As a result, they have a comparative advantage in producing more dirty moving forward. And then there are entrants, there are continuum of entrants, and these continuum of entrants are using this production function, which is convex, satisfying in other condition, and they come up with new technologies. So the financial friction side is the critical part, of course, in the model, and the theory is taking a tractable approach here. They say firms are facing a borrowing cost, RK, and RK depends on the maturity of the firm. K is the maturity, so as K increases over time with some Poisson arrival, R is also coming down basically. So more mature firms are facing lower financing costs. So on the empirical side, Martin already mentioned, they are using the German firms to study the impact of 2008 and 2009 global financial crisis. And they show that indeed those firms that were more exposed to Commerzbank before the crisis, indeed they fixed their exposure to Commerzbank in 2006. Taking this as given, then they say if they were more exposed to Commerzbank, if they had tighter relationship to Commerzbank, then they would be more vulnerable to a reduction in loans. And as a result, they would be more affected, and they are exploiting this variation and showing that indeed the green patterns are responding more. So let me go to my comments, and some of those will be a little bit nerdy theoretical comments. And so first, in the model, why is dirty a bad energy or bad in general? Why is dirty or oil bad? I think, you know, the model was simplifying. So typically in this class of models, there's also there's always a damage function where whenever you produce with dirty energy sources like oil, or when you use dirty technology, then there's emission, and that emission then later on leads to temperature rise, etc. And then there will be this feedback effect. And in this model, there's no feedback effect. So as a result, you know, this O in the production function has no consequence in that sense. So I think it might be nice to add this damage function into the model so that really, you know, a dirty technology or dirty energy is really hurtful. Otherwise, you know, there's really no harm to the society in that case of using O or clean. So I think it would be also important to highlight some of the inefficiencies, because this is a different model, and what are the inefficiencies, and what should the policy, if we think about policy, for instance, what should the policy correct? For instance, these type of financial crises, if there's no damage coming from dirty energy sources, these type of crises are even better, because they are effectively eliminating these premature technologies. And they are already bad, and inefficiently the society is investing money into these premature technologies. There has to be a reason for us to move away from dirty technologies. So that's why without the damage function, I think those discussions would not be really substantiated. It would be helpful to introduce that margin. On the entry dynamics, so it wasn't very clear to me how entry is being determined. So there's continuum of entrance, and there's a convex cost function. And in that case, the number of entrants is indeterminate. Indeed, it goes to infinity. So you want to have as many entrants as possible, and then the entry goes to infinity. Typically, you know, the way to fix this is to introduce not only a convex cost function, but also a fixed cost, so that it pins down the number of entrants. Right now, it wasn't, or you can have also a linear cost, not a convex cost, but linear cost, just like in Aghion-Howitt model, for instance. In that case, you can pin down the entry, but this way it wasn't very clear to me how the entry is being pinned down. And another thing is that, of course, the world is split. Some people, are more into, global warming. Some people are more into energy crisis. But in any case, with oil, I think there's also the exhaustible resource component related to oil. And it would be potentially nice to introduce also the supply of this exhaustible resource, because the price of it will potentially be self-regulating. So how will this influence and have a feedback in the model's dynamics moving forward? When I was thinking Martin's presentation, I think there's also another thing which I didn't include in the presentation here. But the firms here have a very strong incentive to save. So they want to save. And if the model allows for saving, probably this is going to mitigate the detrimental effect of financial crisis on any innovation activity in general. Still, I think there will be an effect, but so it might dampen some of the quantitative effects. And another thing, the paper, the abstract was starting by saying that green innovation offers a solution to climate change without compromising living standards. But in green and dirty technologies, there's always a trade-off, right? You can take all the resources from green and put them all into dirty, and you can grow faster. So you're sacrificing growth in these models by allocating resources into green. So then there is some compromise. So that's why I think it might be important to address that. So I'm out of time. I guess there can be also some streamlining in the model, which we can talk more. Like first, whenever there's an innovation, you don't introduce a product initially. First, you introduce a template, and later on the template becomes a product. It wasn't really clear to me why we need to go through this two-step innovation process rather than having just a standard innovation and a product immediately. And I think I can stop here. In general, it's a very insightful paper on a super important topic. I think that the authors are on a great path to write a very impactful paper. And thanks again. Thank you.